name is Rob, 9.5. We're going to take a look at a little bit of a review here before we start. We're talking about writing some equations. This is the equation of the line. You should recognize that the y-intercept is 1, 2, 3, 4, 5, and the slope is about rise 2 over 1, so maybe 2x plus 5. For this guy, you should recognize this is the square root function, so the general formula for this square root function looks like this, maybe h's and k's. This is the horizontal shift. And it looks like it's over 1 up 1, so I'm going to think that it's 1 square root. It's shoved over 4 units to the right, so maybe x minus 4 and down 1. Remember, whenever you see parentheses, which we don't see parentheses, but it's there in order to type this in the calculator, this would be shoved over horizontal shift 4 units to the right, go the opposite direction. So this one, it looks to the right as well, so this time it's a parabola, so I would say x minus 3, because when I set that equal to 0, I get the root of 3, but it's also up 1, and again, it looks like it's over 1 up 1, so I'll go with the value of a. So you should know how to graph lines, square root functions, quadratics. So why did I do that? Because in this section, we've been looking at rational functions and how to graph rational functions, and what you want to do is look at the numerator and the denominator. From the numerator, we're going to look at x-intercepts, writing equations, and from the denominator, we're going to look at the vertical asymptotes. So for my x-intercepts, it looks like it might even be a triple root, but I don't think it is. I think it's just a single root at x minus 1, and I'll talk to you about why I think that's a single root in just a moment. But my vertical asymptotes seem to be at negative 3 and 4, so that'll give me an x plus 3, changing the sign, and x minus 4. And the reason why I thought it was just to the first, if I put this to the third power up here, then the degree of the numerator would be greater than the degree of the denominator, and I'd have an oblique asymptote. But it seems to me like my asymptote is at y equals 0, and to fit my definitions, then the degree of the numerator would have to be less than the degree of the denominator. And so yes, I think 1 is the degree of the numerator, and the denominator has a degree of 2. So I think my final equation is this rational expression, rational function. This time I'm going to go the opposite direction and talk about how to graph given an equation. So first I gave you a graph and said come up with the equation, and now I'm giving you a function, and again, vertical asymptotes are at negative 5, 3, 4, 5. I got a vertical asymptote here. It looks like I have a double vertical asymptote at x equals 2. Remember, it's not going to alternate. That's going to cause the volcano, and this is going to be at x equals 4. So writing equations, looks like x-intercept is at negative 7. Another x, a double, which means I'm not going to pass. I'm going to bounce through, well, I'll try to maybe this blue point is the bounce. So I have to remember to bounce at that blue. And 1, 2, 3, uh-oh, something's weird here because I can't have a point on vertical asymptote. In fact, that's called a removable, which causes a hole in the function. So you can't cross the vertical asymptote, so I know something's going on here, so I'm going to have a hole somewhere at 4, 0, and I'll come back to you and find that. So really, I'm just looking at this piece of the function then. Don't worry about the hole yet. We'll get to the hole at the end. So I'm going to try to graph this function. I could find the y-intercept as well. In fact, the y-intercept would be very helpful because the y-intercept here, then it would look different than if the y-intercept was negative. Well, let's go ahead and just find the y-intercept by letting x be 0. So I'm just interested if it's positive or negative. So 3 times 7, because if I let that be 0, times a 1, all divided by, this is going to be positive and positive. So I know that the y-intercept is positive, and that's kind of helpful. I don't know exactly what the y-intercept is, but I do know it's positive. I'm going to be passing through this function, so I know it comes down here. I think we decided that this was a double asymptote at this peak, which means if this goes to negative infinity, this side should go to negative infinity. But I can't, because that would create another x-intercept. So I know I have another problem here. And the problem is that that blue dot I didn't pass. This was that double root, which meant I should have bounced at that double root. So this function really should come down. It's a nice bounce right here. It goes to positive infinity and comes over this direction. So remembering the double x-intercepts don't pass, they bounce. So now the function's up here, and looking at the degree of the numerator, I would say the degree of the numerator is 3. There's 3 x's up top. The degree of the denominator is 3. So I'm going to do the a over b to find the horizontal asymptote. And in this case, the horizontal asymptote should be at 3. So now when I start drawing the function, I know I've got this bouncing at 1, goes to infinity. This causes the volcano, because I have a double asymptote here, approaches the y asymptote of y equals 3. And since I need to continue, oh, good, I got a nice little point over here to continue, and I'm passing through here. So this one was good because it had a double vertical asymptote, this pink double vertical asymptote, which causes the volcano, and it also had a double root, and that happened at this flower. So I'm going to bounce at the flower, but I passed at the happy face. All right, and this one says write the equation of this. Oh my gosh, nope, that's the final answer. This doesn't say write the equation. So those are some good examples. Here comes section 5.5. If it's the first degree, then that means that there is one solution. If it's the second degree, that means there's 2 solutions. They might be imaginary, but there are 2 solutions. If it's the highest degree is 3, that means there's 3 solutions. And if it's a 4th degree, it looks like x to the 4th, and that means that there are 4 zeros. So we're just looking at the total number of zeros that we have. For a couple notes in your book, I'm going to slide through those if you're book readers. This is the remainder theorem, which says we just look at the factor and we're going to synthetically, or excuse me, evaluate f at the root. So f at the root will give me a remainder. If the remainder is a 0, then I know I found a root. So if it's not, then I just found a point. In this case, 3 comma negative 14 is a point. My recommendation is, this is hard to evaluate. 3 cubed is 27. Then you have to multiply all this out and get the negative 36. That's difficult. My suggestion would be to find out if this has a remainder of 0, which it doesn't. It has a remainder of negative 14. My suggestion would be x minus the root is always the factor, equal to the factor. So if I were to ask what the factor is, I would say x minus 3. But if I were to ask what's the root, I would just choose the 3, and I would synthetically divide by the root by using the coefficients here, a 1, a negative 4, and a negative 5. So for those people who have never synthetically divided before, you bring down the first term and you multiply. 3 times 1 is 3. Negative 4 and 3 is negative 1. Multiply. Negative 3. This should be a 0. And the reason why that's a 0 is because I have no x terms here. So I need a placeholder of a 0 followed by the negative 5. I knew I should get a negative 14, and I wasn't getting it. So let's try this again. 3 times negative 1 is negative 3. Adding negative 3, there it is. 3 times negative 3 is negative 9, and that gave me the negative 14. Now, even though I made a mistake, I think this is easier than evaluating here. You can choose either method. So again, if it says find the remainder, you could either evaluate the function at 2. My personal preference, you can do whatever you like, is to do synthetic division. I'll see if I can do it one more time to find the remainder. Bring down the first term, multiply, add, multiply, add, multiply, and I think the remainder is negative 1. You can evaluate this to see if it is negative 1. If it is, then the point is 2 negative 1, barring any mistakes I made again. If the remainder is 0, then you found the root, is what it's talking about. So here's explaining how to use synthetic division. So again, if the factor is negative 1, we're going to synthetically divide. If the factor is x minus 3, we synthetically divide by negative 3. And look, no, negative 3 is not a root. It looks like 1 is, though. So here they showed you the synthetic division of 1. So again, use synthetic division. I've been doing this already. It doesn't look like they skipped any terms here. Last time I'll synthetically divide. 2, add, multiply, add, and yay, we found the root. Now what does that mean? That this was an x squared term, so if they were to ask me to factor, then yes, x plus 1 is a factor. But the other factor comes from this guy right here, and this becomes an x squared term. So negative 2x squared plus x plus 3, which if you can factor, I would, and if you can't, then I would try to use the quadratic formula to find the other roots. So this is talking about the degree that it could be at most. This could be an x to the 4th, or x to the 6th, or x to the 8th. It cannot be an odd because the ending behaviors are first and second. This one cannot be an x cubed because I have too many terms. So I have 1, 2, 3, 4 terms. So it's always, here it is, at most, the number, if it's 4 terms, at most it could be, well, it can't be an x cubed because I got too many terms. So it could be an x to the 5th. There's always one less term. So x to the 5th, or x to the 7th, or x to the 9th, or anything higher, but it cannot be an x cubed because I have too many terms. This is Descartes' rules of signs, which says we're going to count the number of, or try to find the number of positive roots and the number of negative roots. So this graph that I have graphed here has no negative roots, it never crosses, but it has all 3 positives. So Descartes' rules, excuse me, Descartes' rules of signs says count the sign changes. So I do flute-de-doops here. So I'm going to start out with negatives, and as soon as I change it, I do a little box or a little flute-de-doop down there. So that's 1 change, 2 changes, 3 changes. So I would say 3 or 1. There's 3 sign changes. 1, 2, 3 sign changes. So there could be any multiple of, there could be a 3. It could cross 3 times, but it could only cross once because maybe the other 2 are imaginary. So if this would have been 7 sign changes, I would say 7 or 5 or 3 or 1. Did I get them all? 1, 3, 5, 7. Yes. So less 2 all the way down to 0. To find these are the positives though. To find the negatives, I would replace x with negative x. And let's multiply. Negative x cubed is negative times this negative is positive. Negative x squared is positive times a positive 3. Negative times negative is positive, and this is positive, so look at that. No. So that's kind of interesting. So that means don't look for any roots that are negative. Either it's scenario A or it's scenario B. Either all 3 of them, or there's only 1 positive. So here they worked it out for you. Again, the rule is replacing x with a negative x to find the negatives. So those are the solutions, I believe. So this is just another practice. Let's count the flute-de-doops. There's 1 sign change, 2, and then here 3 sign changes. That's it. So it could be 3 or 1 positive roots. To check for the negatives, let's replace x with negative x, and I'm just going to write down positive or negative. So if I throw a negative x right in here, this whole thing goes to positive. This whole thing goes positive times a negative is negative. This is a negative. This is positive. Check my math here. Positive and negative. If I did it right, we'll count the flute-de-doops. 1 sign change, 2 sign changes, and 3. So this is also 3 or 1 negatives. And we know that in total there are 6. So it could be that there's 3 positives and 3 negatives, give me all 6 of them. But there's not. In this case, there's only really just 1 positive, and there's 1 negative, and the other ones must be imaginary. Again, another example of Descartes' rules of signs. This is another example of, well, I'll do one more with you. So counting the sign, none. So for the positives, there's no sign change. That's helpful information. For the negatives, I'm going to count, let's see, if I throw a negative in there, it's positive, that's positive, that's positive. There's none, 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 none. Oh my gosh. So I know that for 81, they're all imaginary. It's kind of interesting. So potential rational roots, we're going to do p divided by q. This is the last divided by the first. So I'm going to do the last term divided by the first term. P divided by q is called the rational root theorem. So here comes my last term, which is a 12. I know you think it's a negative 12, but I'm going to do plus or minus here in a moment, so it won't matter. So my p divided by q, I'm going to list the p's horizontally and the q's vertically. All the factors of 12 are 1 and 12, 2 and 6, 3 and 4. All the factors of 3 are going to go down vertically, 1 and 3, and I'm going to start dividing. 1 divided by 1, 2 divided by 1, 3 divided by 1, 4 divided by 1, 6 divided by 1, and 12 divided by 1. And then repeat the process, but this time 1 divided by 3 gives me 1/3. So 1/3 is a possible place where this function might cross the x-axis. 2/3. I'm not going to list 3/3 because I already got it, a 1. 4/3 I better list. 6/3 I already got a 2. And 12/3 I already got it. So here's all my possible rational roots. All I'm going to do is put a plus or minus out front. You can actually list them the day of the test, like the author did. What does this tell me? That without a calculator, I know that this function, whatever the graph looks like, there's no reason for me to synthetically divide by 5 because there is no 5 that's even a possibility. In other words, if I were to synthetically divide by 5, that's not going to be a root. That's what Descartes' rules, the rational root theorem says. Descartes' rules of sign tells me how many positive and how many negative roots there are. The rational root theorem tells me the possibilities. In this case, 5 is not even possible. On your test, since you're not using a calculator, I will give you one root, and then it's up to you to find the other root. So given that -1 is a root, you'd have to list them. Yep. In fact, +1 and -1 is always a possibility for a root because it's always a factor. So here's what I'll do under test. Bring down the first term, I'll ask, find the other zeros. Given that -1 is a 0, which means I better get a 0 here, let's multiply. -3, 5, -5, this is adding to -12. Sure enough, it is a 0. Well, what does this mean? It means that this was an x cubed, and I'm left with 3x squared plus 5x minus 12. And you're left with the task of trying to find factors that remain. And if you can't, you have to do the quadratic formula. So I'm going to look for factors of 3 and 12 that differ by 2, 6, 3, and 4. That differ by 5. And I think I found them. Here they are. 9 and 4. So my first terms are 1x and 3x. That comes from this guy right here. And then after first terms, I'm going to look for outer terms. And the 1 lines up with whatever it tells me to, a 4 it looks like. And then I'm going to go back and the 3's go together. Signs are going to be different. The larger term is positive, and my larger term is my outer terms. No, it's not. The outer terms is only 4x. My inner terms is 9x. So I'm going to make that 9 positive. Oh, it looks like my other roots were -3, and that's a possible. Yep. And the other root was 4/3, and that was also a possibility. So -3, I knew that -3 was a possibility from this, and I knew that 4/3 was a possibility from here. So even though these were possible, not all of them worked. Only the -3, 4/3, and -1 were actually real roots, and I know I have all 3 of them because it's to the 3rd power. The actual graph looks like this. But you found all 3, or we found all 3 roots. Now it would be easy to graph at that point in time. So find the real zeros. Here's what the book says. Go through all these steps. We look at the highest degree to find out how many. Use Descartes' rules of signs to find out how many positive and negatives there are. And then we use the rational root theorem, this p divided by q, to list them all. And then we start attempting to look for zeros by synthetically dividing. It's a long process. So step number 1 says there's only 4 possible roots. That's the highest degree, so I'm not going to look for more than 4. Descartes' rules of sign says count the flukey-doops. Well, there's none, so I'm not going to synthetically waste my time looking for any positive roots. I know that there are none, according to Descartes' rules of signs. To find the negatives, I'm going to throw in a -x there. That still remains positive. Throw in a -x here. Throw in a -x here. That means positive. Throw in a -x. And that stays positive. So it looks like there's a lot. 1, sign change, 2, 3, that can't be right. Is that right? 4? Well, yeah, there could be 4. 1, 2, 3, there could be 4 sign changes, or there could be, there could be 4 negative roots, there could be 2 negative roots, or there could be no, it's possible, this thing is facing up, it's possible that all of the roots are imaginary. It could be that there's only 2 roots and the other 2 are imaginary, or I could have all 4 roots crossing the x-axis. So now it says, let's go test this p divided by q. So if I do the 9 divided by 2, listing all the 9s, factors of 9s are 1, 3, and 9. All the factors of 2 are 1 and 2. The rational root theorem says my possible places that I should be checking for roots are 1, 3, 9, 1/2, 3/2, and 9/2. And remember, it's the plus or minus. So it looks like I've only listed 6, but I've actually listed 12 possibilities because you have to check the positive and negative. don't worry, I'll actually give you a hint on the day of the test of what, so you don't have to sit there and try. How many times do we say? 12 times. You could be taking your test all day. So I'll give you a hint in your test, and I'll tell you, oh, maybe -1 is a root that you should know works. So let's pull out the coefficients, 2, 13, 29, 27, and 9. Bring down the first term, multiply, add, multiply, add, multiply, add. Hey, this is going to work. What do you mean this works? I actually got a 0. So that is to the 4th. Oh, it's telling me that it's a double root. So guess what? You get to synthetically divide by 2 again. So -2, add 9, -9, 9, -9, and it's a 0. So I'm left with 2x squared, because this was an x to the 4th, this is an x to the 3rd, plus 9x plus 9. Now remember, if this doesn't factor, I have to use the quadratic formula. So I'm looking for factors of 2 and 9 that add up to 9. Let's see, I don't think I find them. So I might have to use the quadratic formula. -b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. This will probably happen on your test, so don't be afraid of the quadratic. Wait, this adds up to 9, which means this should have been a 2. Oh my gosh. So my outer terms is 3, my inner terms is 6, and 6 and 3 adds up to 9. So this does factor. Oh my gosh. So you could use the quadratic. I just knew that it was factorable because the square root of 9 was nice. So let's see, 2, they both go to a 3, signs are alike. So it should have been x equals -3 and x equals -3 halves. You would have gotten the same thing doing the quadratic. It just takes longer. -9 plus 3 divided by 4 and -9 minus 3 divided by 4. See, -12 divided by 4. This gives me the same thing as it's -3. And this guy must be the same thing as this. So we found all of our roots. We found all of our zeros, and you should be able to graph it from that. All right, I hope that was helpful. Just discussing Descartes' rules of signs, and the rational is another example where -1 is a double root, so you can practice that one if you'd like. And there's some bounds and some zeros on your MyMath Lab, but I will not be testing over that. So you can read through the notes about finding your maxes and your bounds, but that will not be on your test. So the intermediate value theorem just says if you plug in a value and you find out that it's negative, down here you plug in another value that's positive, somewhere between it must be a 0. So intermediate value theorem says just test 2 numbers, and if you evaluate f at 1 and it's positive, and then you evaluate f at 2, because that's what it tells you, and you're just checking to see if it's positive, there may not be a root, positive, positive. But if it goes from positive to negative, then there's got to be a 0 between 1 and 2. That's what the intermediate value theorem says. Oh, there it is. There must be a 0, because when you evaluate at 1, it's -1. When you evaluate at 2, it's 23. And the only way, so if you have a point over here, 1, -1, and you have another point at 2, 23, sure enough, there's got to be a 0 somewhere in between, a root, and an x-intercept. So again, more book notes. And I'm going to end the video there. Good luck. If you have questions, email me.